Hey everybody, a very cool combinatorics problem that deals with sums and differences here. And so what we have here, if we select 6 random positive integers, we can show that there will always be 2 of them that will have either a sum or a difference that is divisible by 9. Now what I've done here is I've selected 6 random numbers. You could argue about whether they were really randomly selected, I suppose, but there's 6 of them there. And notice if you take a look at the 105 and the 42, I've written them down in quotient 9 remainder form. Notice that 105, the difference, 105 minus 42 here, they both have remainders of 6, which is crucial to the way this proof goes. 105 minus 42, just by the form alone, the remainders cancel, right? And you'll have 11 minus 4 times 9. So that's equal to 7 times 9. We don't even have to say that's equal to 63, right? It's a multiple of 9. We have a difference that is a multiple of 9 from 6 randomly selected numbers. Now, it turns out also, if you look at 127 plus 80, 127 plus 80, and we're talking about the sum operation. Now you see here, difference is this guy right here. Sum is this guy right here. And you can see that 8 plus 1 adds up to 9. But also we have 8 and 14. So that would be 22 plus 1. So this would be equal to 23 times 9. Okay? And again, folks, hopefully you see 8 plus 1 is 9. We have 14 plus 8 is 22, but we have another 9, so that's 23 times 9. So in both cases, we get multiples of 9, and we have a sum and a difference. We're just trying to show there's actually one instance of, at least one instance of this type of thing occurring. Here we had 2 instances of it occurring. And again, y'all, let me clean that up just slightly there. Eraser. Whoops, did I get the eraser? We want that to be a 9 there. Okay, let me get this working again. Okay, so that's 7 times 9. Okay, so again, a concrete example. Now that motivates the following more general approach. Any 2 numbers from the group of 6 numbers are going to have this form, right? Just like up here, in any of the 6 numbers have the form. Well, here you have 2 different quotients, q sub 1, r sub 1, and q sub 2, r sub 2. Those remainders are guaranteed to be between 0 and 8 inclusive, okay? And so you can see we get 5 what they call pigeonholes. This is a famous combinatorics thing. Yes, those are pigeonholes in the background. Okay, but notice that every one of these sum up to 9 except for 0. And that works out nicely also. But what we get here, in this case, 2 of them have to, there were 6 numbers selected, right? 6 numbers are selected, but there's only 5 pigeonholes. Some people, I think, call these categories perhaps. So at least 2 of the 6 randomly selected numbers will end up in one of these pigeonholes. Okay, so from there we conclude that either R1 equals to R2 if they both flock to the same remainder, or R1 plus R2 will equal to 9, which was this case right up here, right? So in both cases, we do get at least one multiple of 9 of the said description. Okay, now just this maybe is a little much here, but notice that if we use these choices for A and B in this notation, notice that A minus B is consistent with our first example. A minus B, the remainders actually cancel, right? These remainders cancel, and so what we would have would be the difference of the 2 quotients. That would be q sub 1 minus q sub 2, right? I love this stuff. This is really cool. In the PigeonHole Principle, it's called other things like, I think, Dirichlet's result, I believe. But anyway, it's a neat name. It's a little too colloquial, but it's still a powerful result. Okay, so there we go. A minus B, you're going to have that happen due to the PigeonHole Principle and the way you can write A and B as a quotient involving 9 with a remainder. Now what about over here? A plus B A plus B would be similar to this. It would equal to Q1 plus Q2 times 9. Q1 plus Q2. And that'll be plus 9. Excuse me, times 9 plus 9, which is clearly a multiple of 9, right? If the sum of two objects are multiples of 9, then the object itself is a multiple of 9. So you see, we can write down QED here. We've proved what we set out to prove. Anyway, I love that one. You guys, please let me know what you think, or you don't have to if you don't want to. I just think it's kind of a neat thing, such a simple result. A simple sounding thing can be very powerful. The key is to figure out how to choose these pigeonholes, you know. But anyway, we did prove what we set out to prove. We'd have either a difference or a sum, you know. So anyway, that is all for now. Thank you for viewing.